So now that we know a little bit about how to model a sequential decision problem in the framework of a Markov decision process, let's talk about how to optimize one. Or rather, okay, we're not going to talk about how to optimize one yet. We will in the subsequent lectures. We're going to talk about what we are trying to optimize. Okay, so here's the picture again of the notation and the characters. We have talked about the Markov decision process piece, the MDP piece. Now we're going to talk about what we expect from the agent piece. Okay, so we already talked about this a little bit. Here I'm going to give a slightly more general form. So given a policy, this policy is what is making the decisions. We're trying to what I should say is, yeah, given this policy, there is this notion, which is called a value function, this V function, which basically tells us how good is this policy, as in how much reward will it get the agent, will it accrue over time. So can read this out. Okay, here's the sum over time of the reward. Okay. Starting from some time t, that's why the tau is starting with t, until the deadline, the horizon, let's say capital T. For the state at that time, the action that we select at that time, plus potentially some terminal reward, some reward for the last time step, given some initial state S and some policy pi. And this is going to be how much we expect to accrue over time. So our optimization problem is going to be to find a good policy pi that actually optimizes and maximizes this function. So this is what this may look like over time. Another way to think about this is we want to achieve the best value. We want to maximize the value to go, not the value of the immediate future, but the value from now until the end of time, whether it's finite or eventually infinite, potentially with a discount. There's also the opposite version of this, which is instead of maximizing value, we minimize cost. And it's the same exact thing. We just have minus signs. We have, we multiply two minus signs. The problem's equivalent, but it has a different interpretation. So stated more formally, we can write down the optimal policy and the optimal value function. So the solution of an MDP is to find an optimal policy, which we often denote by pi star. And this pi star will satisfy this optimization problem here, which is basically to find the best pi within some class of pi, some capital pi, so valid policies. So these could be, say, linear functions, these could be neural networks, such that this value is optimized. This 0 indicates that we're going to start with, say, the 0th time step rather than some other time step for this policy. Okay. And then we're going to take this policy, and when we evaluate it, we actually get the corresponding optimal value function. Okay, so it's written as follows. Okay, so V0 of pi star, we can write as shorthand to be V star, which is the optimal value function. One note, which I want to give a bit of detail on, is on the expectations. There's quite a bit of notation when it comes to Markov decision processes, so we try to simplify some of it, and this is one simplification that we make. The expectations, when we talk about the value function, refers to all possible stochasticity in the trajectory. So here, let me give you an example. So a policy, let's say we apply it to a state, we might get some sequence of state, reward, state, reward, state, reward. And these rewards, they might be somewhat random. The states, given the current state in action, the next state might be somewhat random. The policy itself might also be somewhat random. And when we talk about the value function and this expectation here, we are taking the expectation over all of that randomness. Okay, so there's shorthand in terms of the expectation over all of these next states. If the policy is stochastic, then we also are taking the expectation over the randomness in the policy itself. If the reward function is somewhat random, we're taking the expectation over that as well. So this expectation is doing a lot of work. It is, again, encoding all of the randomness in the trajectories. Okay, so now I want to return to the real-time rideshare matching problem, and I want to put the value function in context of this problem. This slide will be a little bit heavy, and we won't understand in this lecture all of the pieces. Hopefully by the end of this unit, you will have a good understanding. So let me introduce that value function that we just discussed. So the value function being the expected sum of rewards. In this case, we have discount in the sense that we care about future rewards less than we care about present rewards. So this delta that we introduced earlier, we basically said, well, the original reward here does not capture long-term value. We want a version that does capture long-term value. And right here, these are three equations that actually make explicit how do you compute this, this delta, okay? So this delta, you can see, is actually really closely related to the value function, okay, the value function here. It's also related to another quantity, which is actually also called a value function. It's called the Q value. And we'll get into this later. What I wanted to do here is just connect the dots a little bit regarding where does the long-term value come from? The long-term value comes from this expected sum of rewards. Okay, so it might look like, oh, maybe it's the opposite because of this minus sign. But if you look at this Q value is also a function of this value function. Okay, so overall, here we just have, some function of the value function. Okay, the RL methods are basically trying to solve for these quantities, V, Q, and this delta, IJ. Okay, so we'll hopefully this will make sense by the end of the unit. But just to provide a bit of intuition, when we say this, when we have this long-term, when we say we want to capture this long-term value, what you want to think about is this value function right here. Okay, we want to capture which actions we should take to optimize this long-term objective. So in practice, Lyft actually implemented these ideas. They implemented some of these RL algorithms and actually showed their effectiveness. So the most impressive metric is that their unavailability, this is when no match was possible. So we could not find a driver for a ride request. This actually went down by 13% with the RL algorithm as compared to without. So one might argue that this is unavailability is like the worst experience, close to the worst experience that a rider could experience. So from that metric, it's quite good. There are other metrics that they looked at in terms of rider cancellation, 5-star ratings, revenue, and so on. Okay. I want to take a couple minutes now to talk about the policy. The policy is the object that maps states to actions. It's actually what's making the decision. And there's a lot of different forms that the policy can take on. I don't want to belabor it. This slide is quite detailed and quite formal. I mostly want to give a couple examples of what a policy looks like, and let's do this in the context of the Amazing Goods Company example again. So the policy, for example, could be stationary, it could be deterministic, it could be Markov. Okay, and I'll give a couple examples of other policies that could be take on different structures. So what stationary means is that the policy does not change over time. That means that the policy has no time dependence. There's no sort of T subscript. It's deterministic in that there are no random variables here. It's Markov in that it is all it needs is the current state. It does not need historical information. On the other hand, we could have a stochastic history dependent policy. So for instance, here, this is, yeah, so there is some stochasticity, there's a uniform random variable, and there's history dependence in the sense that it needs not only the current state, it needs the current state ST, it also needs ST minus 1. Okay, and so based on this, based on the current state and the previous state, it will determine how much inventory to buy, a random number between filling it up and going beyond that. Sorry, filling it up based on where the inventory was 2 steps ago. So this is basically saying if the inventory in this time step was less than half of what it was in the previous time step, meaning there's a lot of purchases happening very quickly, then maybe I want to take this strategy of stocking up more than I would have otherwise. Okay, so also returning to the other motivation that we had of designing future hypothetical traffic systems. One of the starting points for trying to understand this question of how do we adjust our modeling assumptions, how do we start to understand the conditions under which we can have system improvements, even with a fraction of automated vehicles, we go back to this example that we've seen a couple times now in this course, which is this circular road, very, very simple setting. So what we were able to do is model this as a Markov decision process. What does this look like? Well, we can define a very simple state, which is for a single vehicle, let's define the state as just the relative velocity and head weight. This is actually really consistent with a car following model and what those models take in as input. The action is the acceleration of this vehicle. The reward is, say, the average velocity of the system for all cars, not just for this one vehicle. And the horizon, the time step is 0.1 seconds. The horizon is, say, 5 minutes of simulation time. And then we have a particular algorithm called TRPO, which is one of the commonly used deep reinforcement learning algorithms. And based on this, we can turn the crank of applying these algorithms to this model, this MDP that we have now specified. And here's a video of the outcome. We first have the train controller off so that the traffic waves actually form. And then, the vehicle crosses this dotted line, the vehicle controller turns on. We see that it at first slows down to open up a gap, then it quickly closes that gap. And with that closure of the gap, we see that there are no more of these backwards propagating waves that we saw prior to turning on the controller. And so this was done without much hassle, to be frank. We had to code up this simulation. We had to specify these different parts of the MDP, but then we run the algorithm and we we get the data, we generate this video, and that's that. So with this, we were able to show that RL, which is in purple, basically matches near optimal performance. This is the green dotted line. This is across a variety of vehicle densities, which is the x-axis. The y-axis is the average velocity of the system, so higher is better. And as compared to the state of the art, which is a sort of classically designed controller in blue, RL, without knowing very much, just specifying what to expect, is the data that you're looking at, what is the reward function, the algorithm was able to identify a near optimal controller. Good. So I'll skip through the details a little bit. We were also able to interpret some of what's going on. So here, to provide a bit of interpretability, we can look at the degree of acceleration. Recall the action as acceleration for 3 different models. Here we have a deep neural network, a linear model, as well as IDM. So maybe let's ignore the linear model for the time being. We can see that IDM is actually a lot more aggressive. You can see that the amplitude of the values are much higher than the values in the deep neural network. So the IDM model is decelerating and accelerating much heavier than the deep neural network. We can also see that we did need a deep neural network. If we use a linear model, we were not able to capture the same range as we see in the deep neural network. So using these same ideas, we return to the clip that I showed earlier. We could, again, model the sequential decision problem for each of these different scenarios by specifying the state space, specifying the action space, specifying the transitions, which is given by these the traffic simulator, specifying the reward and the horizon, and then applying these algorithms to see the potential impact of mixed traffic with a fraction of vehicles automated. Okay, good. So I think I'll skip these pieces. So the last thing I want to do is just walk through one more example problem of modeling a Markov decision process. This is an emergency medical service, EMS vehicle problem. So this is also in the mixed autonomy setting. So we have an EMS vehicle. These EMS vehicles, they really need to get to their destination. It's usually an emergency. And there is a relationship between how quickly these vehicles can get to the destination and mortality of, say, the passenger on this vehicle. So it's really important that we get these vehicles to the destination. And one problem that came up is, could automated vehicles actually assist these EMS vehicles in getting to their destination? For instance, at an intersection, perhaps some vehicles could help clear the road such that the EMS vehicle can clear each intersection more efficiently. So I wanted to also bring this up because this is a project that actually originated as a class project a couple of years ago, and now is a published piece of work. Dajiang, who is the lead author here, is now an assistant professor at ASU and has also helped tremendously with this course in the past. So let's take a look at this problem. The question is, should the AV take maneuvers to assist the EMS vehicle in crossing an intersection? So let's consider a specific scenario. We have a right lane where the EMS is currently located and it's fully congested. An automated vehicle can sense nearby. It can also communicate with the EMS vehicle. The goal of the AV is to assist the EMS vehicle to reduce its travel time in crossing this intersection. So the exercise is to define an MDP to model this problem, including the state space, action space, transitions, reward, and objective function. Good. So just putting the previous question in this this loop. So let's talk through what the state space might be. Well, the state space for the AV might be the headways, the speeds of the vehicles, surrounding the AV, in front, let's say also behind, as well as the position and the speed of the EMS vehicle. Potentially what would also be helpful is the traffic signal phase information. When is the light going to turn green, and so on. The action space might be similar to some of our other examples, the acceleration, deceleration, the whether to hold the speed, whether to change lanes to the left, whether to change lanes to the right. The transitions will depend on the actions of the AV. Vehicles may move randomly, or perhaps according to some driver models such as IDM, perhaps some intersection dynamics. So here we often won't specify the transition fully for complex systems. We'll say, okay, it's encoded by some simulation model. The reward might be, say, the real-time speed of an EMS vehicle, or the overall travel time of the EMS vehicle. And then the overall objective function is really the same for all these problems. It is the sum of rewards over time. And there will be often a discount factor. Here, we're going to keep a pretty high discount factor. And the reason for a high discount is that we do care about getting, if the vehicle does not get to its destination, then there may be poor consequences. So we care about the reward over each time step, not just the ones earlier in time. So we'll have a very high discount factor, some discount that's very close to 1. Okay, good. So this was an introduction to Markov decision processes and more broadly, how to model sequential decision problems as MDPs, how to think about sequential decision making and the techniques of reinforcement learning in the context of transportation and what value it can bring. Closing with some references, and I'll see you next time.